Hello everyone, my name is Raphaël and today I'm excited to tell you about my work using atmospheric pressure to improve geolocator positioning. As you know, atmospheric pressure varies with altitude. That's why pressure measurements taken by geolocators are used to estimate birds' altitude. But what we've missed is that pressure also varies with time. Indeed, if you've been looking closely at this video, you'll have noticed very small temporal variation. These temporal variations are actually quite big if we remove the altitudinal component. And thanks to weather reanalysis data, we now have access to high-resolution data worldwide of 1 hour and 30 km by 30 km. You've probably guessed where I'm going with this. How can we use atmospheric surface pressure data to improve the spatial accuracy of geolocator position? This study applies to multi-sensor geolocator, which in addition to light also measure atmospheric pressure and birds' activity with an accelerometer. But before diving into our approach, I'll briefly recall the standard procedure to extract activity information and location from light data. In this study, we use 16 tracks from 9 different species showing a wide range of migration strategies. But for the purpose of this presentation, I'll focus on the example of the Eurasian wryneck. The first step is to use the accelerometer data to estimate birds' activity. Based on the intensity and the duration of the activity, we can determine period of migration with high temporal precision of 15 minutes. The two key information we take out of these steps are, firstly, the duration of flight for each migration period, and secondly, the identification of stationary period when the bird is assumed to be stationary at a single location. The second step is the traditional approach to estimate position based on light intensity measurement. Based on a fixed threshold of light, we determine the twilight at the bird's location. Each twilight allows to draw a line on which the bird was located, so that two consecutive twilights provide a point on the map. A major limitation with this method is that there is a large uncertainty, and that this uncertainty is actually very difficult to estimate, because the light intensity measured on the bird is subject to its environment, such as the topography around, the vegetation or the weather, but also its behavior, if it's nesting or singing on top of a canopy. Fortunately, we usually know the location of the bird at equipment and retrieval site, which allow us to calibrate the twilight error. However, this can only account for part of the error. Secondly, because we get a sample only every half a day, this approach cannot provide a realistic position of stopover lasting a few days. Let's look now at the proposed approach to get position from atmospheric measurement. Here is a time series of pressure measured on the wryneck. You can see the long stationary period after equipment at the wintering site and at the retrieval, which in this case is the same as the equipment. In between there are two migration periods composed of short stopover and high altitude flight corresponding to this large drop in pressure. But let's zoom in the first stationary period. Because we know the location of the equipment site, we can retrieve the pressure time series of the weather reanalysis data called ERA5. We observe a striking match of their temporal variation. But there is still a significant offset in the absolute value of pressure. This can be explained if we look at the fine-scale DEM SRTM 30 meter within this ERA5 grid cell. A wide range of elevation exists within the grid cell. But in this case, we actually know the exact location of the wryneck within this grid cell and can translate the ERA5 time series to that specific elevation using the barometric equation. The resulting time series shows a perfect match in both the temporal variation but also the absolute value. Now let's see how we can use this information to produce a probability map for each stationary period where we don't actually know the location of the bird. To illustrate this approach, we'll look at the first stationary period and compare the ERA5 time series at two different locations, one in dark blue in Paris and the other one in light blue in Czech Republic. The probability map that we are building combines two distinct information. Firstly, a time series mismatch, and secondly, an elevation masking. So firstly, we want to compare the temporal variation between the geolocator and all Area 5 grid cell. But because we don't know exactly the altitude of the bird within that particular grid cell, we ignore the altitudinal component and shift the time series so that the mean error is 0. We can then compute the RMSE between each time series and convert it into a probability map, assuming a Gaussian distribution of the errors. Here is the resulting probability map. Second, we can check that the range of pressure measured by the geolocator can correspond to the altitude range present in each grid cell. To do that, we first compute the minimum and maximum altitude within each grid cell using a defined scale DEM. We can then translate the Area 5 time series of pressure to this minimum and maximum elevation, in this case illustrated in green and red lines for the location in Paris. We can then simply check if the time series falls in between the two lines. If so, as in the case for Paris, we keep the data point. But if not, as in the case for the Czech Republic, we exclude this grid cell by masking the probability map. Repeating this procedure for each grid cell produces a map of possible location for our birds. Because this approach does not need calibration, we can use the known location at equipment and retrieval to assess its precision. To do that, we simply look at the distance between the known true location at the equipment site and the most likely position in the pressure probability distribution map. In this case, it's only a grid cell apart of 30 km. We can compare this distance with the one from the light data, which is around 100 km. We can do the same for the last period at retrieval, where both are quite good, and repeat this procedure for the 16 different tracks. The light data has an average of 117 km error, while the pressure is 53 km. This distance is even smaller if we exclude the mountainous species. Note that light data is actually calibrated on this location, and that the error is expected to change with latitude and time of year. Let's have a look at the overall trajectory of the Wryneck by comparing the distribution map from pressure with the probability map from light data, as well as the distance covered to the next stationary period using the flight duration and assuming a distribution of speed, illustrated here with 5 and 15 meters per second. The next stationary period is a relatively long stopover, where the light data provide good longitudinal information, but not very useful latitude. The pressure data show a well-defined location matching both the flight duration since the equipment site and the light data. The bird performs another stopover before reaching its wintering site. It then flies back to its breeding ground with a stop around Paris, and then arrive at the same location as it departed. In this example, we only look at stationary period of at least 2 days. The next and final step is to generate a trajectory path with a Markov chain Monte Carlo, which allows to combine the static probability map of pressure with the light data, as well as the transitional probability of flight. Because the conditional probability map of each stationary period can be computed easily, it is convenient to use a GIP sampler, faster and more accurate. Here is the resulting trajectory of our Wryneck, including all stationary period longer than 12 hours. Don't look too much at the white line and dot. The real information is in the posterior probability map, illustrated with a different color for each stationary period, and the intensity of the color corresponds to the probability of presence of the bird at this location. The circle is simply the mean position of the probability map and is not always realistic, while the size of the circle illustrates the duration of stay. We can look at another few tracks, in this case the Hoopoe, crossing the Mediterranean Sea. And here is the trajectory for the Eurasian nightjar, migrating in multiple small flights, all the way to Congo and back. And this is the map for the Woodland Kingfisher, an intra-African migrant from South Africa to Sudan and back, and finally the great reed warbler. In conclusion, the main output of this approach is to improve the precision of the bird's position of at least twice better than before. This level of precision at the regional scale opens several avenues of research. For instance, we can now know each bird's wintering site within 30 to 50 kilometers. In the case of this great reed warbler, we can identify it as being the Waza National Park. This can help identify sites to be protected or understand bird survival and breeding success in relation to their wintering site. Secondly, we can estimate the full journey of the birds for any stopover duration and study in greater detail the bird's migration strategy. Finally, this work highlights the benefit of integrating external databases. Adding wind data, rain, or temperature may help better understand the driver of migration of each individual birds. Thank you for listening to my talk, and feel free to get in touch if you have any question.